All right, so let's review. The first part of the video will be your answer key. So first question, define and differentiate clearly between computer architecture and computer organization and give 3 examples of each. Many of you, as I was looking around, and this is very common, it's okay, you're progressing properly, you're on your way, this is fine. A lot of you kind of remembered visible, transparent, so you probably wrote something to the effect of parts of the computer that are visible, parts of the computer that are transparent. The way the grading will break down on the 13 points will be 3.5 for each definition and 1 point for each example. So if you put those down for the 7 points, you'll get approximately 3. I think you'll probably get 3. So you're on the right path. The actual definition, does anybody remember the word-for-word definition for computer architecture, or really close? Suddenly a lot less confidence in the room. System attributes of a computer that contribute to its logical execution and are visible to the programmer. I didn't see any invisibles. That made me very happy. I jump up and down, and someone will still make that mistake every time. But so hopefully that's the case. And what are some examples? I saw some people put the correct examples. Yeah, I/O is one of them. Data representation. Someone else. Instruction set architecture. Memory addressing, right? So those are the ones. What's computer organization? I heard somebody mumbling over here, approximately. I'll start calling on people if I don't get an answer. Yeah. CPU. Okay, CPU. Mm-hmm. What's another example? ALU. What's another example of organization? Memory technology, right? So why is organization the memory organization, and why is the memory addressing, and why is organization the technology? Going back to the definition of organization. You change the address of code because the definition of computer organization is what? It's not invisible. It's Windows Defender. Okay, close. The definition of computer organization is physical details of the computer that are transparent to the program. So number 2, state clearly Amdahl's law with an equation and discuss its significance. What's the equation? So that's exactly right. So the execution time of new is equal to the affected divided by speed up plus the unaffected time, right? And so second part, why is it significant? So I'm sorry, you guys are my superstars up front. So anybody else? I hear you whispering. All right, this is how I'm going to start learning your names again. Because you guys, you two are not paying attention. Come up front. You two were not paying attention, so now you get to answer the rest of the quiz in front of the class. Come on. I'm not asking now. Oh. So, there's 2 pieces of, here we go, here's 2 pieces of chalk. So yeah, you guys are going to help me out with the rest of the quiz. So what is the significance of Amdahl's law?
I don't remember.
You don't remember?
Yeah.
What was the equation he just said?
I don't know.
Yep, because you weren't paying attention. That's right. That's why I got here. So no, you stay here. Okay. So go ahead. When you tell him again what you just told me about the definition, and when he's going to tell you, you're going to write it up on the board.
Okay.
So
execution new. Equals affected over speed up.
Yeah, but just use an equal sign.
Oh.
Yeah.
Affected over speed up.
AFFECT. Affected.
F.
Affected. AFF.
F.
Here.
Oh. Yeah.
There you go. Very good. Exactly right. That's a perfect score. So your turn. What's the significance? Why is this equation significant as being you want to be an electrical engineer, right? That's why you're in here?
Yeah.
Yep. So this is an important design concept. So who actually knew the right answer? Why is this significant? Alex. So Alex, can you explain that? So he's going to tell you the answer, and I want you to write it on the board, okay?
Well, I'm really good because it lets us identify the limitations of the given operation.
Correct. All right. So can we break that explanation down a little more simply? Explain to somebody who doesn't know the answer.
Yeah. Okay. When you make a given change to your implementation,
I'm gonna cut you off. So the simplest way to put it, this is the classic engineering overthinking, right? So this is the reason I'm doing this. The reason why we have these quizzes is because teaching the concepts is harder than you think. So sometimes you have to break it down even more simply. So the moment the implementation of the computer, running through the calculus equation, so the simplest way to put this is that improvement of one part of the computer does not affect the Colton computer by that same amount, right? So so now you're going to tell everybody what I just said. So you're the professor now. So you see why? Because improvement of one part does not. There's a reason why the equation has the word unaffected in there, right? Does that make sense? You almost there? 3 more words. The entire part. The entire part. Or the entire computer. Okay, there you go. That's a perfect answer. Right? Good job. So does anybody have any questions on 1 or 2? All right, so part 3, we have a CPU running at 2 gigahertz. It runs a CPU running at 2 gigahertz runs a program with the following instruction counts in CPU times. Or that should have been CPIs. CPI 2, 20, 5, 5, 1. So most of you got up to here. So you knew that 20 times 2 plus 5 times 5 plus 1 times 10 plus 1 times 10 plus 3 times 5. And you probably realized really quickly that these questions are always going to add up easily to, in this case, it was 100, right? So what's the unit of this number 100 here? That's cycles, right? So when I was dropping the hint about check your units, that's because I saw a lot of people putting 100 as the answer to this. So you're halfway there. So what's the other part of this that you need to do? Divide by the number of instructions, right? So you have 20 plus 5 plus 10 plus 10 plus 5, which comes out to 20, 40, 50. So that becomes 100 over 50, which is equal to 2. So that's your answer, right? So the CPU time of the program, right? So you have number of cycles, you have the cycles per instruction, and you have the number of instructions and how the clock rate, right? So in this case, CPI would just be times the number of instructions. So what you're able to do is just do 100 here, because if you were trying to do this with the whole equation, it'd be 100 divided by 50 here. and then you'd be multiplying it by instructions, so you'd just be multiplying it times 50, right? So then you have 100 times what? So you got cycles. So what we're trying to get to, since it's time, it's seconds. So we need to use seconds per cycle times cycles, right? The units will set you free, which is equal to 1 over 2 gigahertz times 100, which is equal to 50 times 10 to the -9 seconds, right? So that's the CPU time. Does that make sense? I did see a number of people put this, so a lot of people are on the right path. So then the last part, and a lot of you got this right. State the improvement in performance if the CPI of integer instructions is improved from 2 to 1. So you took this part, you realize it's the same number of instructions, so the instructions cancel out, right? So normally you'd be doing this over this. So you have the original equation here, and then you have the same thing here, except you're multiplying it by, you're changing it from 2 to 1, right? Well, you can see really quickly that these go away, since they're the same. So we also knew that up here that this was equal to 100, right? And so this is equal to, well, subtracting 20, so it just becomes 80. Now this is where I was telling you to leave things alone, because this equation, or 100 or 80, when you get to that point, just leave it alone. Don't mess with anything. Because then people start putting it's an improvement of 20%, which is not true. I mean, it happens. It's a quiz. It's pressure, right? That's the reason why I'm doing it this way, is because I want you guys to think, oh, okay, in this kind of situation. Ultimately, I want you to demonstrate that you have the knowledge. I'm not trying to test your ability to do, certain levels of mathematics. So it turns out that this is actually 5 over 4, which is actually 1.25, or an improvement of 25%, right? But on your exam, good enough. Better is the enemy of good enough, right? So does anybody have any questions about what we did? Remember, this is the big thing. Show up, stay in class, take your quiz. I will always reward your effort, right? All right. So on that note, does anybody have any other questions about performance before we move on? And if you recall from at the end of last lecture, I asked you all the same question about, do you all have any questions about performance? Are you sure? So if you hear that at the end of a lecture, right? All right, so remember this from last lecture. We're talking about multipliers and multiplications. So now what we're doing is we're just doing the same thing, kind of taking the philosophy of Hobbes and adding or subtracting a number of times. So in this case, we have, let me bring up my EpicPen app here. We have this addition going on here, so we add it, we do a bit shift cycle. If it's a 0, we don't add. If it's a 1, we add over and over and over again. And then we ultimately get our multiplication. So how does this actually work in an algorithm? So I did add a little note here. This is not something you'd need to know on an exam, but for those of you who are planning to take an algorithms course, the fastest known multiplication algorithm is known as the Kara-Struve algorithm, which multiplies 2 n-bit numbers in big O of log 2 base 3, or n to the 1.5625585, which is, of course, faster than n squared. However, it uses a divide and conquer approach, but here's the issue, is that it's prohibitively difficult to implement in hardware, meaning that you have to add in so many, or if you recall from carry look ahead, you have to have propagate and generate logic in order to make it run fast. In order to make this work in hardware, you'd almost have to have an entire computer. It's pretty ridiculous, but it's really, really fast. So that's where you have your good design requires good compromise coming into play. So here we know that we have to have n plus 1 bits of space because we need to have a sign bit. We're going to perform n iterations that would overwrite the sign bit, giving incorrect values. So we have to make sure that we do things the correct way. So this is a signed multiplication. Up to this point, we've only talked about unsigned multiplication. So come on. There we go. And that, nope, that's a little too far. So here is the actual signed multiplication algorithm. As I indicate here, you can, on an exam, when I ask this kind of question or a quiz, you can expect that the number that I will give you can be represented in 4 bits. I will not give you, 64. I will not give you 128, anything like that. So, if you remember from our multiplication, right? Which one's the multiplier and which one's the multiplicand? So if I have 6 times 4, which one is which? Yeah. Multiplicand, plier. Very good. So this is multiplier, n plus 1. For those of you who have coded in C or anything involving arrays, this is the length of the array. So if it's n equals 4 here, that means n plus 1 is going to be 5 bits. So if I had 15, it would be 0, 1, 1, 1, 1. Why would I want to have n plus 1? Yeah, sign bit. Okay. Likewise with multiplicand, it's 2n plus 1, right? Why do I want 2n plus 1? Recall from the diagram I just showed you? Yeah, you're going to be shifting everything over and you're going to have this maximum value of potentially having 2n plus 1. And then you'll have some sort of result product, right? So the way an algorithm notation works is you have your inputs and your outputs like a function, right? You have written functions and you have what you're passing to the function and what you're returning. So that's what's going on here. So first thing we do is we set product of 2n. In this case, in the algorithm, we assume that the least significant bit is 0. So if it's 2n, that means we're talking about the most significant bit, right? So the most significant bit of the product is going to be equal to the XOR of the most significant bit of the multiplier and the most significant bit of the multiplicand. And the reason we're doing that is if it's 0 and 0, that means we want it to be 0, our multiplication is going to be positive. If it's 0 and 1, it's going to be negative. 1 and 0, it's going to be negative. 1 and 1, multiplying 2 negative numbers gives me a positive value. So here, this is the rest of the algorithm. So we're going to go from I equals 0 to n. So we're actually going to do this n plus 1 times, right? And we'll be able to see a couple of examples of this here. If the least significant bit of the multiplier is 1, then we're going to add the multiplicand and the current product. So it's the same thing if we had 10, we'll do 16 times 12 here. So 16 times 11, that'll actually be a better analogy. So if we did 16 times 11 in base 10, if we did 1 here, actually even better, 101. We did 16 times 101. First we'd have 16, then we do the bit shift, right? And then we'd have 0, and then we have this multiplier again. If it's 0, we're not doing anything. If it's 1, we're testing this bit. So that testing the bit here is this stage. And that's 1, so you add 16 again. Right? So then it gets 16, 16 as our result. Same thing, if we're multiplying 1001 and 1101 here, we'd be testing the most significant bit. Be 1s, be 1001. Do the bit shift, test the least significant bit of the multiplier. In that case, it's here. So this shift the multiplier right bit by 1. What that means is 1001. So we test the least significant bit of the multiplier, 1001. We right shift, which means the least it now becomes these, and we're adding a 0 here. Does that make sense? So then we're testing the least significant bit here. Then we shift left the multiplicand, do the product, so it becomes 0. And then we right shift here, so it becomes 1, 1. So it becomes 1, 0, 0, 1. Right shift the multiplier, left shift the multiplicand again, 1, 0, 0, 1. And then our solution is down here, 1, 0, 1, 0, 1, 1, 1. See how that worked? So that's actually physically how it's working. Does this algorithm make sense? When I was taught this course initially, they just threw up this table and we went, oh, what is that? What is that? So here, you don't have to, also I should note, I probably make that note down here at the bottom somewhere. Oh. On an exam, I don't expect you to rewrite every value at every step, right? So there's a lot of these where you see how they're the same over and over again. The only time in a table you'd need to write the value is when it changes. So I'll actually show you which values need to be changed, right? So in this case, we are multiplying 8 times negative 9 using signed multiplication, right? So n is 4, so multiplier is n plus 1 is 5 bits. The multiplier is 9 here, but it's also negative 9. So we do the 2's complement, and that becomes 1, 0, 1, 1, 1. And so our step 0, if we go back to our algorithm, the first thing we want to do is we want to exclusive OR the most significant bit of the multiplier and the multiplicand, and that result becomes our new product, right? So as you can see here, everything that I have written in red, those are the only things you'd actually have to write on an exam. See how that works? So test step 1, we test the multiplier, right? So we test that value here. And in fact, you wouldn't even really need to test it. You can actually read it. So you have if it's 1, we're actually going to add the multiplicand to the multiplier. See here we have 0, 1, 1, 1, 0, 0, 0, which is 8. This number here comes from there. Does that make sense? So you initialize it, you set it up, you add it, the product, and here we've added it together because the least significant bit is 1. Next, we left shift the multiplicand. So you see here how this number's been left shifted by 1 bit. And then we right shift the multiplier. So we see how everything's been shifted this way. Correct? Next, we test the least significant bit. It's 1. We add it. See how we've added it again here? Left shift. See the left shift going on here? Then we right shift the multiplier here. See how if we left shift this here? And what you do on these most significant bits on an exam, typically what you're going to want to do is just keep the same value as the sign bit. Because if this was 8 times 9, then you have 0, 1, 0, 0, 1, right? And if you right shift it, it becomes 0, 0, 1, 0, 0. So as long as you do that, it's fine because it won't affect the algorithm. So again, we test the least significant bit. So here, if for those of you writing this down on the homework, it's perfectly okay to leave all of these parts blank. See how these are all the same? Don't have to include those. See how these are all the same? Don't have to include those. In fact, you can kind of just do what I did here and do like little, or you can just leave them blank. Same thing here. You see how all of these are the same? You don't have to write them.
So we're making the exact same table, we're just leaving those spots.
Yes. I think that would be a tremendous waste of your time. All right, so we got to this stage. It is 1 again, so we're going to add. You see how we're starting to get this value here? That becomes our sum. We left shift the value here. Again, we have the multiplicand. Then we have the right shift the multiplier. Now we're at the most significant bit. And we kind of just do the same thing for the last 2 stages, right? And then here we check this value here, right? We take the 2's complement. We get 1 of this sum here, which is 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, 0. Take the 2's complement, we get this value, which is 72, which is 8 times 9. So if we take the 2's complement of that, it becomes 8 times negative 9, which is our correct answer. So basically what this table is representing, and when you're doing this on your homework block, the only parts that are red are really the parts you have to write. You have your original multiplicand and multiplier, and you're taking that and putting them in the product, right? Add the multiplicand if it's 1. If not, do nothing. That's everybody's favorite part of these algorithms. I don't have to do any addition. Left shift the multiplicand because it's just like just like the conventional multiplication. You want to add it with a 0 at the end. Right shift the multiplier because that's the bit that you're going to check. So that's what's physically going on in your advanced digital system, and you're going to repeat. Does that make sense? Does anybody have any questions about that? Yes.
So,
By the way, this is a joke I like making every year. Right after the first quiz, suddenly whenever I say, does anybody have any questions, that's suddenly when a lot of the questions start flowing. So.
So in like step 1.4 up there,
Mm-hmm.
so when we shift over, or when you like shifted right, are you shifting that sign bit right too? Is that why there's a sign there?
Mm-hmm.
Okay, and then you keep.
I just picked that as a convention. So basically, this is the common question I get when you're doing a negative number. So in this case, we have negative 9, right? And I tell everybody right shift. So that becomes 1, 0, 1, 1 from this part here. So then the question is, what do I put there? Ultimately has no impact on your algorithm, but you have to have some kind of placeholder. And what I tell students is just put in the same value as the sign. And some people will just do this. They'll actually just go 1. They'll do this, and this is fine. 1, 0, 1, 1, 1, and then they'll go 1, 0, 1, 1, 1, 0, 1, 1, 0, 1. This is acceptable too. I won't talk points. As long as you indicate that these are the parts of the algorithm that you know. Ultimately, what I want you to put on the exam is the thing that 1 makes you feel the most comfortable, 2 takes the least amount of time, 3 demonstrates that you actually know it. So, yeah. Any other questions? All right. So then we're going to do the same problem, except with negative 8 times 9. Just to show what's going on here. So we start out, we do the same thing. We initialize our values. Remember the multiplicand is, remember the 2, so this, so this is what happens when you want to do 2's complement, right? 2's complement of 8 somehow always comes out to 8. But then you have to up the sign bit. So here you have this sign extended value for the multiplicand. So this is why all of these are 1, because we have negative 8. But as you can see, they start going away as we do as they do the bit shift. So we initialize, we check our least significant bits, and it becomes a 1, right? And then we test the multiplier, least significant bit. So in that algorithm, it's mplier 0, right? That's what that notation means. It is a 1, so we're going to add it. We're going to add the multiplicand to the product. Then we left shift the multiplicand and right shift the multiplier. Here. Does that make sense so far? So then it's a 0. So guess what? Y'all get to do nothing. Woohoo! Just move on to the next one. Left shift the multiplicand, right shift the multiplier. Step 3 here, we test the multiplier. It's 0. So we left shift the multiplicand, right shift the multiplier. And then step 4 is a 1. So we're going to add this multiplicand here to this one. And it comes out here. That's our solution. Then we left shift the multiplicand, right shift the multiplier. Stage 5, we tested 0, so it's nothing, right? Then we left shift and then right shift. So let me tell you which ones are perfectly fine to write out here. So you have to write out these, right? Make sense? So then if you have an add, you should add the new product. Then you should draw the new left shift and the new right shift, right? So let me put in green all the ones that you don't need to write. Anything that doesn't change it at all, leave blank. So let me ask you a question. Why do I want you to draw or write out the left shift and the right shift every time?
So that you understand.
The course is Advanced Digital Systems, and what I want you to do is demonstrate that you understand shifting, because that's what's physically going on in the Advanced Digital System. So again, here you can go away, write that. That's shift here. So you see how a lot of these end up kind of going away when you simplify everything? Here you got to add it. So you're going to want to do some kind of notation to keep track of what they are. And then does that make sense? I will put it, this is an example of me putting a lot more detail than I expect you to have. Yes, I.
So on tester quiz, you're gonna have to put it in like a table format.
Yeah.
Like this.
I do want you to indicate what's physically going on. Yes.
In step 4.2, when you add the cans,
Mm-hmm.
there's an overflow.
Yeah.
Why does he get rid of that? Or
Oh, just because it's ultimately it's the sign. We take care of that. This is a good question. Okay, so here we have 1 1 1 1 1 1 0 0 0, right? And then we have we're adding this here, right? So you have 1 0 1 1 and then a bunch of zeros. So here it becomes 0 1 and then this value goes away, right? So think back to the topical guide objective where I was talking about overflow and when you're allowed to have overflow and when you can't. Yeah. So basically, we do that by testing the sign bit.
and the computer just knows when
Yes.
to get rid of that.
Mm-hmm. Yes.
And how to make sure the project the sign is to compare the modifier and the sign.
Yeah, so you do that in the very first step, right?
Yeah.
So you do this and you do the exclusive OR. Do you know what the exclusive OR is? Okay, so the exclusive OR is a logic function that states that you take in two inputs this case A and B. And then, so if we do A and we do a truth table, exclusive OR means it's true if and only if one of them is 1, but not both. So F is the output. If it's 0, 0, obviously that's 0. If it's 0, 1, one of them is 1, so that's 1 and 0, 1, 0. So in this case, we have 0 and 1. And this makes sense because 0, 0, and 1 and 1, if you're multiplying two negative numbers, you're going to get a positive number, right? If you're multiplying two positive numbers, you're going to get a positive number. Okay. Any, yes?
Just, is the, so the 4 ones, like in the initialized stage under the multiple can, those are just convention again?
Yeah, that's what's known as a sign extension. Do you all know what sign extension is? I'm doing a lot of assuming you guys know things that you don't know. So sign extension, let's say I have a 16-bit number, right? Which, if you recall from your I-type, well, no, we haven't done I-type insertion. Let's say you have an 8-bit number. That'll be a little faster. And that 8-bit number happens to be -3. So if you have -3, we know that 3 is, actually let me do 5 because I think 5 is a little more clear. We know that 5 is 101, right? And we know that the sign bit would be 0. We also know that if we do this, it becomes 010, 011, and then we have our negative, we have a sign bit here, right? But if we're storing this in an 8-bit value, what is the rest of these going to be? More importantly, how do we do this in the event we have some sort of addition? So let's say I want to add -5 and 7. So I have 0, 1, 1, 0, 1, 1, 1, right? And we're going to stop the TGOs here, but I'm just going to answer this question and you'll all be dismissed. So I would be adding 0, 1, 1, 1, 1, 0, right? So if adding 7 and -5, if I'm adding -5 and 7, we're getting some sort of that. So if I have a 4-bit value of 7, right? Right? And then I have -5, which is, we determined that's 1. Right? We need to have some sort of carry value. So it becomes 1, I'm sorry, it becomes 0, 1, 0, 0, carry it over here, right? So if we keep going here into an 8-bit value, what's going to end up happening is that carry is going to come here and it's going to come 0, 0, 0, and 0, right? So it becomes 0, 0, 0, 0, 0, 0, 1, 0. So -5 plus 7 becomes +2. So what's happening here is in a fixed architecture like RISC, where you have a fixed instruction length, you have to be able to ensure that you're getting the correct sum. So in this case, if it's 8 bits, we do a sign extension to ensure, because if it's a positive number, it will be all 0. If it's a negative number, it will be all 1s. And that way, if you add them or subtract them together, you will get the correct value because they will carry out. And then we use the principles that we know about adding and subtracting sign values to know that we can or cannot have an overflow. Did I answer your question? Does everybody understand that concept? Okay. In that case, you are dismissed.